I'm Alex. I'm here to talk about Metamorph, a tool to synthesize large objects from Dafny specifications. This is joint work with Sasha and Jeff. Sasha unfortunately cannot come and give the talk. So I first want to talk about the motivation of our synthesis hacks. Testing in object-oriented language context may require setting up complex objects that has private fields. So you can only set the field to the desirable properties you want by a set of methods associated to the object. So the challenge here is to generate programs, mostly a sequence of method calls without complicated control flow that produce objects with required properties. So our idea is to use method specifications in the verification-aware setting. In particular, we're using Dafny to guide the synthesis. So let me walk you through Dafny through this small example that we're going to talk about. Dafny is a verification-aware, semi-automated language where the user guides verification by writing pre- and post conditions. So here, the post condition is written with ensure clause, where it's assumed after calling the method. And preconditions written with requires are always needs to be proven before you invoke the call. Important thing, so here's a social network database kind of like example where we have users modeled with natural numbers. Each user associates a set of friends in the set of friend requests. And the constructor, for example, constructs an empty map of users. We have other methods like adding a user to the social network database, removing a user, sending a friend request, and responding to a friend request. Another important thing to note is that Dafny uses SMT solvers for verification. Namely, verification success is an unsat from the SMT solver, and a verification failure can result in a satisfiable assignment, where the assignment is a counterexample from the verification query. Another two things to note is that here we use a ghost field to model the heap state. This is not available at runtime, so this is, echoes the private field that I introduced before. Another thing to note is the method bodies are hidden from hidden for here, which might be an external function call, can be implemented in Java or C#. And this is also some of the key ideas of Dafny to have modular verification. It only reasons with method specifications. So you don't need to look into the method body. So let me give you an example synthesis problem. So here with the social network database, we want to synthesize a clique of 3 users, which all of whom are friends. Here we write our synthesis goal as we have the 3 users, 0, 1, and 2. 1 is friend of both of them. So here we have an object invariant saying that if I'm a friend of you, then you will be a friend of me. And then user 2 is user 0's friend. So what is a sequence of method calls that can generate this desirable heap state? So it's pretty simple, right? You add 3 users, send 3 requests, and respond to the 3 friend requests. However, this is actually like a non-negligible larger calls to a bunch of methods. So we can remove the primitive arguments to all of the method calls and try to ask Dafny to generate the concrete arguments to these things. This already takes minutes. And this is already given we have provided the sequence of method calls. In particular, when we are trying to synthesize this program, this is unknown. So how are we going to synthesize large objects that needs dozens of method calls to get to the desirable object state? So here comes Metamorph, which we kind of performs a goal-directed backward synthesis. So we're, instead of generating everything all at once, we do things step by step, limiting the solver context. And another observation we have is the synthesis goal is a object state that satisfies the desirable properties you want, and it's also a conjunction of constraints. So we can reconstruct method arguments and prior object states from verifier counterexamples by doing this step-by-step thing. We generate concrete intermediate heap states to step through the backward search. We also guide the synthesis to minimize the number of unsatisfied constraints, where we introduce 2 distant metrics. I'll talk about that with a concrete example. So here's our example. We are still synthesizing the clique with 3 users. So we are performing a backward synthesis, so we should look at the target state first, and we're trying to backward synthesize it to the initial state, where we just call the constructor when we have an empty map. So here we take one step, so we consider all of the method calls that is possible. And here for simplicity, I only list 2 out. So requesting one step away from responding to a friend request, one step away from removing a user. And we can ask the Dafny counterexample generation to synthesize the concrete heap state, which is the state where user 2 needs to respond to user 0's friend request, and the state where, state 2 where, oh wow. Ooh. Okay. State 2 where we need to remove the extra user 4. So here is obvious, right? We should explore state 1 because it is closer to the initial state. But how we are going to have a systematic approach for this idea? So we introduced the piecewise distance metric, piecewise distance metrics to encapsulate this idea, where we reason about the lower bound of method calls required to go from the initial state to the intermediate concrete object state. So here, for example, state 1, we need to at least have 3 calls to add user. Here we use some pre-trainings with Dafny to reason with how the method specifications interacts with our conjunction of constraints. So now we can reason that add user can at most add 1 user, and no other method calls can have anything to do with adding users. So we need at least 3 calls to add users. We need at least 2 calls to the request respond. And we need at least 1 friend request, which has a lower bound of 6. I want to note that this is a lower bound. We actually need 8 calls from the initial state to get to the state 1. However, for state 2, we need to at least have 4 add user calls and at least 3 response for friend request, which adds up to a lower bound of 7 calls. So now it is obvious for Metamorph that we should explore S1. So we will go and continue and take it step by step until we reach to the initial state, where we just add the user and then the synthesis is done. So we evaluate Metamorph with a number of APIs, including some basic data structures and some more involved examples adopted from prior work. We compare Metamorph with a bunch of different ways of performing synthesis. So our baseline is we ask the Dafny verifier to prove that no program generates a desirable object using the counterexample generation process to synthesize the sequence of method calls all at once. So this is a solver context problem. And then we have Metamorph without the distance metrics to guide the search. And we have 2 different metrics. One is the piecewise distance metrics that I just introduced before. The other one is the greedy distance metrics, which only reasons about the number of constraints that a method can change. So we do not invoke Dafny to reason about how it really interacts with the conjunction of constraints. So here is the evaluation we have done on the social networks example I've introduced before. So the y-axis is the running time in log scale. The x-axis is the number of interconnected users in the target object that we ask Metamorph to generate. So this is basically the number of users in that clique. So you can see that the baseline, even though it performs synthesis pretty fast for a smaller number of objects, it doubly exponentially blows up when we are considering anything that is larger than 2. Similar things happen for Metamorph without a metric to guide a search, because it will always consider junk state where we just like remove a user, so we have 1, and we just get farther and farther away from the initial state. And here you can see that the 2 metrics we introduced actually don't differ from each other that much. This is because we have strong object invariance on the social network database, where there's really not much states that we can explore. So instead, we have another case study that we relax the object invariant. And here, the greedy metric will consider unreachable states. And similar to the Metamorph without any metric, it will just get lost in some unreachable states, or it will just get farther away from the initial state. So in summary, we introduced Metamorph that uses counterexamples to reason about effects of method calls. We proposed 2 distant metrics to guide a search over object state. We evaluated Metamorph on 8 APIs, And it can synthesize programs up to 57 method calls, some of which are not even automatically verifiable without user hint. We found that Metamorph performs better when a distant metric is used, and the piecewise distant metric is better than the greedy metric in some selected cases, like the one I introduced before. At last, we also prototyped an integration of Metamorph with the Dafny testing framework. All right, that's my talk, and I will take any questions. Thank you.
Yeah, please.
Thanks for the interesting talk. My question is mainly about the concrete maybe implementation or maybe the algorithm. But did you try to deal with symmetric breaking? Like in your example, the 3 nodes are symmetric, and no matter you operate on one of them, then it's equivalent, right?
So yes, we have a generalized precondition method that is described more in details in the paper, where we try to generalize the constraints that we're considering. So yes, like there are states that are basically the same, and yeah, we do need to work around with that.
Thanks.
A very interesting talk, thanks so much. I'm actually not from this area, I don't know the details, but it seems very much to me as A star, and you know,
yes.
in A star search,
exactly.
heuristics have to be optimistic. So I was wondering if you have this result for your heuristic functions, that the distance they estimate is always less than what it actually is.
So the reason I use distant metric rather than heuristics is because in the paper we have a more detailed comparison between A-star search and best first search, and we have some discussions over there. So I'll refer to the
my
paper.
question was whether you have a proof that your heuristic
We do
is
not have a
optimistic.
proof of the lower bound, but we do have a sketch of what the distant metric is trying to show.
Okay, thanks so much.
Thank you.
Yeah, thank you for the paper. So in this backwards search, you need to make solver calls. Hey, did you do any analysis of, like, are there particular calls that took a really long time and the rest were fast, or was it similar for each step in this process?
So we do have a verification time breakdown that is described in the paper. I'm not aware of like there's like one particular method. I mean, it's Dafny. Anything takes a very long time. But yeah, we have a breakdown where we kind of the context of this is because like you cannot just ask Dafny to generate everything because it will just takes forever. But yeah.
Well, I guess I was curious, like even within a particular example, is it the case that one of the steps takes a really long time and then others are shorter, or is it more evenly distributed?
I think it is more evenly distributed, but I need to refer to the synthesis time breakdown, or the time spent on solvers by different procedures.
Sure, thank you.
Thank you.
Okay, no more questions? Okay, I think that's the end of this session. Let's thank all the speakers for the session for the great talks.